Hello students, welcome to the GCC physics class today. Last class la enna paathirupom appadinengana potential, definition of potential and potential due to a single charge, then potential due to a dipole paathirupom. In the continuation we are going to see today these three topics: equipotential, topic number 1, equipotential surface. Second topic, relation between electric field and the potential. The third one is potential energy due to the collection of charges as well as for the dipole. The first topic is equipotential surface. Equipotential surface. So what is meant by equipotential surface? The name itself gives the answer. The surface which is having the same potential is known as equipotential surface. Now let us consider a charge. Let it be positive charge. So this charge will give the electric field that we know already. I am assuming a point. This point is at a distance, say r. So due to this charge at this point, what is the potential? So what is the formula for potential? So V equal to 1 by 4 pi epsilon 0 Q by R, correct? So Q by R. So the potential at this point, say the point is A, is V equal to 1 by 4 pi epsilon 0 Q by R. If I assume a point here, let it be B. This point is also at the same distance, say R. What is the potential at B due to this charge is V equal to, once again, the constant 4 pi epsilon 0 Q by R. See these two cases. At the point A, potential is this value. At the point B, potential is this value. All are same. So A and B are having the same potential. Not only these points, if I consider the point here, say all are having the same distance. So these points will have the same potential. Now this surface consists of different points A, B, C, D, E. For example, all the points are having the same potential. Now you can say this surface is an equipotential surface. So the definition of the equipotential surface is, it is a surface having points which are at same potential. So this is the definition of equipotential surface. This is for the charge. So does it have only one equipotential surface? No. If you assume still a greater distance, say this distance, say this distance is capital R. So if you draw a spherical surface surrounding this is also having the same potential. Likewise, you can draw any number of spheres surrounding this, all are said to be the equipotential surface. So the equipotential surface for the given charge is the concentric circles here. So of course here it is a 2-dimensional, so we are saying that it is a circle. In the case of 3-dimension, it is called a sphere. Okay. So now for the uniform electric field, let us assume uniform electric field. In the case of uniform electric field, what is the equipotential surface? It won't be a spherical in nature. Suppose you consider the points here, all the points will have the same potential. So if this is the line, if you consider a plane surface, say the rectangular plane. Now this rectangular plane surface is known as equipotential surface. So, for the uniform electric field, the equipotential surface is a planar surface. So, likewise, we can have the number of equipotential surfaces. Next, we are going to see the properties. Next, we will see the properties of equipotential surface. Now, let us assume the point A and B in a given equipotential surface. If a unit charge is moved from A to B, so along the equipotential surface, the charge, unit positive charge is moved from A to B. So, what is the work done? See, the formula for work done is charge into then the potential difference between the 2 points. So, what is the final point? Final point is B, initial point is what? A. Okay. So, now in this case, we have assumed the equipotential surface. So, the potential remains same, VA equal to VB. Then, if you substitute this condition here, the both will cancel. So, what you will be getting is the work done is 0. So, now we can say this is the first property. The work done along the equipotential surface is 0. This is property number 1. Property number 2. The electric field E vectors always perpendicular to equipotential surface. Potential surface. This is a condition. The direction of E always perpendicular to the equipotential surface. Suppose if it is not perpendicular, what will happen? So, if it is not perpendicular, it has an component, electrical field component will be there. Due to that, there may be a difference in the electric potential. So, the value of electric potential may not be 0, then the work done may have certain value. What we have seen in the first property is work done is 0 in the case of equipotential surface, but in the second property, suppose if the electric field is not perpendicular, means there is some work done. So, there is a contradiction. So, immediately what we can say is, sir, the electric field always perpendicular to the equipotential surface. Okay, this is about the first topic. The second topic, the relation between electric field and the potential. Let us assume the uniform electric field. This is uniform electric field. In this uniform electric field E vector, a unit positive charge is moved from one point to another point like this in the opposite direction. Say, let the distance between the 2 points be dx. So, when the unit positive charge is moved against, so definitely there will be a work done. What is the formula for work done? Sir, work done is, so force into distance, correct? Here E into dx. Why? Force is nothing but, I have changed F into E because force acting on the unit positive charge, E into dx. Since the distance is small, work done is also small work done. So, here, then put minus. Why minus? The negative sign indicates that the work is done against the electric field. Okay, so this is the small work done. Say, as per the potential, we know that the work done is nothing but the potential. Since the work done is a small work done, it is nothing but the small potential, dW equal to dV we can write. So, this can be changed into this dV minus E into dx. So, E equal to, if you transfer the terms, minus dV by dx. So finally we are arriving the formula E equal to minus of dV by dx. This is called negative gradient of potential dV by dx. Distance, the potential, change in potential by distance is known as the gradient of potential. Since minus sign is here, we have to say the electric field, otherwise known as the negative gradient of potential. This is for the one. Suppose if you consider the three-dimensional case, the electric field vector can be written as dou V by dou x I cap, dou y j cap plus dou V by dou z k cap. See, this is for the one dimension, that is for the three dimension. Now let us see one problem based upon the relation, that is E equal to minus dV by dx. A graph is given. It is a graph between the distance x and y axis potential. So the variation of potential with the distance is given. The question here is, we have to plot the graph, or we have to change the graph between electric field as a function of x. So using this formula, we are going to convert the potential into electric field. Okay, so now you see the graph. Since only the variation is along the x axis, so only x axis, it is one dimensional one. So this is the formula for three dimensional one. So in this case, the j cap and the k cap will be 0. So only one. So E equal to minus dV by dx, that is along x axis alone. Okay. Now we can divide this graph into three sections. First, the potential increases, then remains constant, then decreases. So for the first portion, say first case, so dV, what is the value of dV? Change in value. So what is the final value? Final value, it is given as 25. So final value is 25 minus initial value is 0. Okay, that is equal to 25. What is the value? Change in the distance. Here 0, final is 1. 1 minus 0, that is 1 minus 0, that is 1. So E, therefore E equal to, what is the formula? dV by dx. What is dV? dV is 25 minus 25 by 1, that is equal to minus 25. What is the unit for the electric field? Unit is volt per meter. Volt per meter. Okay. Say for the second portion, which one is the second portion? This constant portion. Say in this constant portion, the change in potential is, say the potential at this point and the final point, remains same value. There is no change at all. So the change in potential is what? 0. So what is the change in distance? 4 minus 1. dx is 4 minus 1, that is equal to 3. So in this case, E, what is the value of E? 0 by something, sir, 0 by something, that is equal to 0. This is the condition number 2, or the part number 2. Part number 3, the last section. So the distance increases, potential decreases. In this portion, see, what is the change in potential? So final potential is 0, the starting potential is 25. So 0 minus 25. So what is the change in distance? Change in distance is 5 minus 4. 5 minus 4. This is minus 25. This is 1. So E equal to minus of minus 25 by 1. That is equal to plus 25 volt per meter. Okay. This is also volt per meter. It's a constant. So the three parts is over. Now we have to plot the graph. between what? The electric field and the distance. This is a graph. Since it is having both positive and negative values, I should take the graph like this. What is the maximum value? 25. 25. What is the negative maximum? Minus 25. Let me take it is 25. This is minus 25. This is E value. Y axis E is taken. X axis the distance x is taken. This is 0, 1, 2, 3, 4, 5. The distance. Now, for the first case, what is the value of E? Minus 25. 0 to 1, minus 25. For the second case, it constant, that is between 1 to 4. 1 to 4, the electric field is 0. Between 1 to 4, the electric field is 0. That means it is changing from minus 25 to this 0. Okay. The third one is the value of E is what? Plus 25. So here 4 to 5 like this, 4 to 5 plus 25, it remains constant. Join this. That's all. So we have converted the potential versus distance into electric field with a function of x. Now we are going to see about the third topic, that is the electrostatic potential energy due to the collection of point charges. See, now let us assume a charge is, say, Q1 is brought from outside and placed at here. Since there are in the vicinity of this region, there are no charges, the work done is 0, because it experiences no force at all. So the work done, we can say work done is 0. Okay. Now when the charge is placed here, if I brought another charge, say Q2, if I brought another charge in this, nearer to this, it is brought up from the infinity. Now this charge will experiences a force due to this charge, that is Q1, because this charge will give the potential at this point. At this point the potential is V equal to Q1 by 4 pi epsilon 0, say R. If I assume this distance is R, the potential at this point due to this charge is what? This value, V equal to Q1 by 4 pi epsilon 0 R. If I bring the charge Q2 here, so there should be work. The work is done against this repulsive force due to this electric field Q1. Okay. So that work done, what is the formula for work done? Work done is the charge. Which charge you are bringing? The charge Q2. The charge into the potential created by the first charge. What is the potential created by the first charge? This is the potential, that is Q1 by 4 pi epsilon 0 R. So you can write W equal to Q1 Q2 by 4 pi epsilon 0 R. This is nothing but the energy, which is represented by the symbol, say U. So U equal to the potential energy between these two charges is nothing but Q1 Q2 by 4 pi epsilon 0 R. What is R? R is the distance between the two charges. Now let us consider for three charges. What is the potential energy of the three charges? Okay, say the first charge is, say, Q1 is placed at A. What is the work done? Sir, when the first charge is placed at A, there is no force at all, no field area, so the work done is 0. In this case, work done is 0. Correct. Another charge Q2, this produces a potential. Remember, this charge produces a potential, say V. In this potential, another charge Q2 is brought and placed at this point, say B. When this charge is placed at the point B, between the two charges there exists a potential energy. Let us assume the distance between the two charges is, say, R. To distinguish, it is the distance between first charge and second charge, so R12. So, what is the potential energy between the two charges? The potential energy between the two charges, U equal to Q1 Q2 by 4 pi epsilon 0 R1 R2, sorry, R12. This is the potential energy. So, remember, when the second charge is brought nearer, it experiences only one field. So, the one potential, so Q1 Q2 by 4 pi epsilon 0 R12. Okay. Now, the third charge, let us assume the charge is Q3. The third charge is brought and it is placed at C. The charge is Q3. When the third charge is kept at C, now the charge Q3 is experiencing two forces, one due to Q1 as well as what? Q2. So, what is the work done in bringing the charge from outside infinity to this point? Say, it has to overcome these two forces. So, the work done formula for this is, work done is the charge Q3 times the potential between what? The first charge as well as second charge. What is the first potential of the first charge? Let me take it is V1C plus V2C. So, V1C is the potential at C due to the first charge, V2C is the potential at C due to the second charge. Now, let us take this distance as R13 because first charge, third one. This is the distance between the second and the third, so R23. Now, what is the work done in bringing the third charge Q3 times V1C? So, what is the formula? Potential is Q1 Q3 by 4 pi epsilon 0, sorry, Q1, it is Q1 by 4 pi epsilon 0 R13, Q1 due to the first charge. Potential due to the first charge means Q1 by 4 pi epsilon 0 R13, the distance. What is the potential due to the second charge? Sir, plus Q2 by 4 pi epsilon 0, this distance. What is this distance? R23. Now, the work done in bringing the third charge, that is at C, we can say it is. So, Q1 Q3 by 4 pi epsilon 0 R13 plus Q2 Q3 by 4 pi epsilon 0 R23. So, this is the formula. This is the force between the two charges. For the collection of charges means we have to combine this equation 1 and equation 2. So, the entire electrostatic potential energy or the work done, total work done is equal to, what is the formula? Q1 Q2 by 4 pi epsilon 0 R12 plus this work done, Q1 Q3 by 4 pi epsilon 0 R13 plus Q2 Q3 by 4 pi epsilon 0 R2. If you want, you can take 1 by 4 pi epsilon naught outside, because it is. So Q1 by Q1 Q2 by R12 plus Q1 Q3 by R13 plus Q2 Q3 by R23. This is the work done. This work done is nothing but the energy, which you can change into the letter U. So the total electrostatic potential energy due to the 3-point charges is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12 plus Q1 Q3 by R13 Q2 Q3 by R23. This is nothing but the electrons. See, since the electrostatic force is a conservative force, what is the meaning of conservative force? See, it does not depend upon the path in which, in any way you can say. Say, first I have taken the charge Q1, then second charge Q2 is brought, third charge is brought finally. Suppose if you keep the first charge as Q3 first, Q2 is brought nearer Q3. In any way, if you find the total energy formula remains same. Now we are going to see the problem using this electrostatic potential energy. So the problem, you see the diagram. There is a collection of charges. Charges are assembled in the way. Each and every corners of the cube, the plus q, minus q, plus q, minus q is placed. The side length is A. We have to find what is the work done to assemble all the charges, first one. The second point is, suppose if any charge is brought or kept at the center of the cube, what is the extra work or the work done in placing the charge exactly at the center, we are going to discuss. Okay. Now, let us assume the corners are P, Q or S. So, the first case, when the charge is plus Q is placed at B, no other charges, assume that only the charge is placed at P. No charges are in the vicinity. So, what is the work done? No potential. So, the work done at P, the work done is equal to 0. Because there is no potential, the first placing the first charge, work done is 0. The second one, suppose second one is this case. So plus q is here, and this point the minus q is brought at the point q. This distance is A. When the second charge q is brought at q, so what is the work done? Work done formula is what? Sir, work done equal to the charge which we are bringing. What is the charge? Which charge we are bringing? The q, minus q we are bringing closer to plus q. So, minus q times the potential due to the positive first charge into potential due to first charge. Okay. So, what is the potential due to the first charge? Sir, first charge is plus q. So, q by 4 pi epsilon 0, the distance. What is the distance here? Distance is A. So, q into q, q square minus q square by 4 pi epsilon 0 A. This second case is over. Now, the third case. Third case, what is the third case? The first charge, the third charge, here is the first charge, here is the second charge, this is point P, this is point Q, so this is plus Q, this is minus Q, this distance is A. So, third charge is placed at R, this charge is plus Q. When we are bringing the third charge here, this will experience the force due to plus Q as well as minus Q. Two electric field is acting. So, this distance is here. So the work done, this is plus Q. Work done at R, WR. So the charge, which charge we are bringing? That is plus Q. Q into potential due to what? Plus Q and minus Q. So both are acting. On this charge, both the potentials are acting. We have to find. So Q into, first, what is the potential due to this minus Q? Sir, minus Q by 4 pi epsilon 0 A. The distance is A. Okay. Then next, plus potential due to this plus Q. Q by 4 pi epsilon 0. The distance, which distance? This distance you have to calculate. The distance between P and this point is R. So this resembles the Pythagoras. You have to use the Pythagoras theorem. A, the value is 2A square. The value of PR is what? The square. The square is 2A square. The value is root 2A. This distance is root 2 times A. So the distance root 2 times A. Is it clear? So Q times potential due to both the charges, Q into potential due to this minus Q, I have written here, potential due to plus Q. In the case of this distance, see, you have to use the Pythagoras theorem and you have to find the distance. Now, you take Q outside, Q into Q square by 4 pi epsilon naught A. So, minus 1 plus 1 by root 2. This is the work done in placing the third charge at the point, say, R. Correct? The last one. The last one is now, what is the work done? Work done in placing at S, W. When we place the last charge, that is minus Q, at this point, this will be experiencing the field due to this charge as well as this. So, the work done formula is the charge. What is the charge? Minus Q times potential due to the charges at P, Q, R and all. So we have to we have to use the potential. So W at S, work done at the point S is minus Q times 1 by 1. So what is the potential due to R? So Q by 4 pi epsilon 0 A, right. What is the potential due to P? So this distance is A. So plus Q by 4 pi epsilon 0 A, right. Plus the potential due to this minus Q, potential acting on this charge due to this minus Q. So minus Q by 4 pi epsilon naught, yes, 4 pi epsilon naught, this distance, like in the third case, say the distance is what? The distance is root 2 times A. So root 2 times A. That's all. 3 potential. So the work done at the point S is, take all the Q outside. So minus Q square by 4 pi epsilon 0 A also you can take outside. So the 1 plus 1 minus 1 by root 2. That is equal to minus Q square by 4 pi epsilon 0 A 2 minus 1 by root 2. So this is the answer. So we have calculated the work done in placing the first charge, the second charge, and the third case. Finally, the collection of charges. After assembling 4 charges on the corners of the cube, what is the final work done? Then what is the second part? What is the extra work done? If another charge, say Q dash or something, is kept exactly at the center, what is the work done? That is the next question, the part number 2. Say again, what is the formula for work done? The charge into potential due to all the 4 charges. Say this is plus Q, this is minus Q, this is plus Q, minus Q. So work done is, for the second case, work done is the charge which is placed at the center times potential due to all the charges. So Q into 0. Why 0? Because both the charges, the potentials are cancelling each other. So the potential due to all the charges exactly at 0. Now the work done is 0. So there is no extra work done. There is no extra work done for the second case. The next topic is electrostatic potential energy of the dipole when it is placed in the uniform electric field. Say uniform electric field. If the lines are regular or parallel, then you can say it is a uniform electric field, say E. In this uniform electric field, the dipole is placed in the, say, perpendicular direction like this. This is plus Q. Assume that this is plus Q, this is minus Q. Now, electric field, this side is positive, this side is negative. What will happen? This positive is attracted by this, experiencing the force towards this. So the force acting is E into Q. Similarly, on the charge minus Q, the force acting is minus EQ. Two equal and opposite forces are acting, so there is a torque. If two forces are acting at different points, what we have to say is a torque. Torque acts on the dipole and it tends to align the dipole in the parallel to the electric field. So it moves. Finally, it is coming and resting like this. Let us assume this is minus Q, this is plus Q, making an angle theta. Right. The dipole distance is say 2a. So I repeat, in the uniform electric field, dipole is placed. Then on the edges, two equal and opposite forces are acting. This due to these two forces, a torque is set to act, and this dipole will move towards, or it wants to align with the electric field, parallel to the electric field. Now let us assume the torque is given in the opposite direction, changing the dipole from one angle to another angle. The initial angle is, say, for example, initial angle, say theta dash. The final angle, say theta. Say a torque is applied in the opposite direction to the electric field. So it is, the torque is acting on the dipole. So another torque will be acting. There is an work done. What is the work done? Work done is nothing but the force acting against the force. Here the torque is against the electric field. Definitely there should be a work done. What is the formula for work done? Say in the case of dipole, the formula for work done, that is W equal to, so integral the initial angle to final angle, say tau into d theta. So in the case of linear motion, force into displacement, here torque into angular displacement. The tau, this tau you can say external torque. Say one torque is given by the electric field, that is torque due to electric field. Now I am turning in the opposite direction, that is called the external torque, that is called the work done against the electric field. So torque against the electric field is equal to, if you find the magnitude, it is equal to torque due to the electric field. Say both the magnitudes are same, only the direction is differing. So what is the formula for torque? Torque is P vector cross E vector. P vector cross E vector. So it's a cross product. So the value is PE into sin theta. PE into sin theta. Now you substitute here. The work done is work done equal to integral theta dash to theta. So PE sin theta d theta. So this work done equal to P and E are constants. Since it is a constant, it can be taken outside. So integral sin theta d theta, theta dash. So what is the answer for this integration? Sir, minus cos theta, theta dash theta. So apply the limits, upper limit minus lower limit. So PE, even you can take minus outside or minus here, cos theta minus of minus cos theta dash. Upper limit minus lower limit. Now P minus PE cos theta plus PE cos theta dash. So this is the formula for work done. This work done against the electric field is nothing but what? Electrostatic potential energy of the dipole, which is denoted by the letter say. So electrostatic potential energy is minus PE cos theta plus PE cos theta dash. What is theta? Theta is the final angle. Theta dash is an initial angle. Okay. Suppose if you assume the initial angle is like this. So what is the angle? Angle is 90 degree. So in this case, if the initial angle is 90 degree, theta dash is 90 degree, cos theta dash equal to 0. Then what is the formula for potential energy? Minus PE cos theta. Minus PE cos theta. This is the final formula for electrostatic potential. If you assume the initial angle is the perpendicular direction, then theta dash becomes 90, theta dash equal to cos theta dash equal to 0. That is the final formula. Here minus PE cos theta is coming, right? The potential energy is maximum for which case? Minimum for which case? See, the potential energy is maximum. See, minus is there. So cos theta should become what? Minus value. Cos theta எப்போ minus value வரும் அப்படின்னீங்கன்னா, substitute theta equal to what? Theta equal to pi 180. Cos 180 is u equal to minus PE cos theta. Suppose if the dipole is moved like this against the electric field, if it is moved in the opposite direction, then in this case theta equal to pi 180 degree. So minus of PE into minus 1, that is equal to PE. This is the maximum value. You can say it is the maximum value. So for the energy to be maximum, the angle should be 90 degree, from 90 degree to 180 degree. What is the minimum value? Minimum value means you take theta equal to 0. This is case number 1. Case number 2. If you substitute 0 here, theta equal to 90. Theta equal to 90. That is initial case itself. Then in this case, cos 90 equal to 0, then the energy becomes what? 0. This is the minimum energy. This is the maximum energy. This is the minimum energy in the case of dipole, electrostatic potential energy of Next, the sum regarding the electrostatic potential energy of the dipole, that is given in example 1.16. A water molecule having the electric dipole moment, the value given is 6.3 into 10 power minus 3 coulomb meter. The number of molecules contained in the water is 10 power 22 given. See, the condition is the dipole moment, all the dipole moment are aligned parallel to the electric field, The electric field magnitude is given, say 3 into 10 power 5 volt per meter. Okay. Then the question is, how much work is done in rotating from 0 to 90 degree, So, what is the formula for work done? The change in potential energy, the final is 90 degree minus the energy at 0. So, what is U? U is an energy at the final stage. This is an initial energy. Okay. Then, what is the formula for U? U equal to minus PE cos theta. So, the final is 90 degree, initial is 0, then substitute here minus PE cos 90 minus PE cos 0. The value of cos 0 is, the value of cos 0 is 1. So, minus PE cos, minus here 1 minus and minus becomes what? Plus. Then this will go off because cos 90 value is 0. The formula is PE alone. This is the work done formula. So, multiply P and E. What is P? Electric dipole moment. So, work done is 6.3 into 10 power minus 3 into, what is the magnitude of the electric field? 3 into 10 power 5. 3 into 10 power 5. So, 3 into 3, 9. 6 3s are 18. 18.9 into 10 power 2. This is the work done. See, remember, this is the work done to rotate only one molecule. How many molecules are given? 10 power 22. So, total work done is number of molecule into work done for single molecule. So, the answer is 10 power 22 into 18.9 into 10 square. Correct? 10 square. Oh, 30. Sorry, it is 30. The problem, it is given 30. So, 30 minus 25, here minus 25. The value is 6.3 into 10 power minus 30. So, 10 power minus 30 into 5 minus 25, 10 power 22 into 18.9, 10 power minus 25. So, answer is 18.9 into 10 power minus 3 joules. Since it is a work done, the answer is what? Joules. This much of energy is spent in rotating the molecule from 0 to 92. That's all, students. We'll see in the next class. See you.